All right, welcome back. So I have one more slide with regards to the Joule-Thomson coefficient. And again, I show you here the same equation, which is the definition of the Joule-Thomson coefficient in here, which is given by this expression. If you actually look at the bottom expression here, which is the denominator of this, this equation, you can see that this is just simply the real fluid heat capacity. Okay, here we split it into two components. One is the ideal gas heat capacity, and then the corrective term if the fluid is in an ideal. And so these terms down here are just simply lumped into a single term here, which is the heat capacity Cp. Now, so for us, in order to determine whether a fluid is heating or cooling as it passes through this Joule-Thomson effect, is to calculate this slope in here. And so you can see that this is given by this partial derivative in these terms here. And the job really is finding an appropriate equation of state that describes the fluid that you are working reasonably well, and then finding that partial derivative using that equation of state and see whether the slope is going to be positive or negative. And that's basically what we need to do. For example, if you have an ideal gas, you can see that the volume for an ideal gas is RT over P, and this partial derivative here is going to be the partial of V with respect to temperature at constant pressure, so it becomes R over P. You multiply it by T, so it becomes RT over P, but RT over P is the same thing as in volume, so you have volume minus volume over Cp, and then that's just simply 0. So if the fluid is given by the ideal gas equation of state, this slope is going to be 0, and so which means the fluid will neither cool nor heat up if you are using that equation of state. However, for non-ideal fluids, we have a general expression that we have derived in chapter 1, where volume is given by ZRT over P, where Z is the compressibility factor. Now we can write this partial derivative here, which is the Joule-Thomson coefficient, in terms of this expression in here. So what we need to do is we take V here and we plug it there, which is ZRT over P, and then we solve this partial derivative from this expression. Just remember that this partial derivative here is evaluated at constant pressure. So it is how volume varies with temperature at constant pressure. So when you do that, when you take the partial derivative, pressure is constant because you are evaluating it at constant pressure. R is a universal gas constant, so it's a constant. So the only two terms that are left here are really Z and T. And so you can expand Z and T using the product rule of differentiation. And then if you simplify it, you will end up having mu JT expression given by this. So here you have RT squared over PCP, and then the partial derivative of the compressibility factor with respect to temperature at constant pressure. So as you can see, for the case of an ideal gas, Z is always 1, and so this derivative becomes 0, and regardless of these other terms, mu JT is going to be 0, which is exactly what I explained it to you a little bit earlier. The TA will show you a couple of examples on how you can use these equations in order to determine whether a particular fluid is cooling or heating. In your notes as well, if you look at page 62, there is an excellent example there. It used to be a midterm question for a number of years, and now I decided to give it as an example, and I want to make sure that you actually understand that problem and you can solve it the way I have solved it there. Now, while we are talking about the Joule-Thomson coefficient, there is actually another way to cool a fluid, and that is adiabatic expansion. In adiabatic expansion, the thermodynamic property that is kept constant is the entropy. And the same way that the Joule-Thomson coefficient tells us whether a fluid can cool or heat during expansion, the adiabatic expansion also tells us exactly the same thing, except that the process is taking place at constant entropy. And so we have seen the entropy equation previously, and since the entropy is kept constant, you can set ds to be 0 and rearrange this equation, and this actually gives you another temperature and pressure relationship in terms of the constant that we are dealing with, which is entropy. And so that is equivalent as saying T over Cp delta V by delta T at constant P. So here you have this partial derivative again, then you can evaluate it from an appropriate equation of state. And so now we have two equations that both are used to cool a particular fluid. In designing a cooling system, you can actually pick and choose which one of these two equations are more applicable, and obviously one is more efficient than the other, and you of course you will figure that one out when you get into the assignment problems which are already posted. I think there is one specific question that asks you which one is more efficient in terms of the process. All right, so I'm going to stop in here now, and the next video clip will start talking about the speed of sound. Thanks.